Today we will discuss different filters. In electrical circuits, we have a device called filter. What is a filter? In a simple language, we can say that a filter is used in electronic circuits to block or allow a select frequency to the circuit. So we can say a filter is often used in electrical circuits to block or to allow a select frequency to the circuit. Let's assume we have a filter here and it has input and output. Input can have like a frequency range between 0 to infinity, but we can define the characteristic of this filter. This filter only allows for the frequency greater than f0 to pass through the filter. So any frequency that passes this filter should be greater than f0, or we can say that the output frequency of course is between f0 and infinity, or the filter can allows the frequency less than f0. Okay, depending to the type of the filter, each filter allows or blocks certain frequencies from like going through the circuit. Okay, uh, we have two different types of filters. We have passive filter and active filter. Passive filter and active filter. What is passive filter? The passive in passive filter, the circuit contains only resistor, capacitor, and inductor. Okay, so the circuit, I mean the filter circuit, contains only a resistor, capacitor, and inductor. Okay, and these filters cannot supply gain greater than 1. So first is first it says that the filter contains resistor, capacitor, and inductor, and the output signal, the output frequency, if we look to the amplitude of the output frequency, is less than the amplitude of input frequency. The gain is not greater than 1. So the output amplitude has to be less than input amplitude. Okay. The other type of the filters is active filter. These circuits contain only resistor, capacitor, and op amp. Okay, so they don't have inductor, there is no big deal, but what they have in addition of passive filter, they have op amp, which is very important. Why it is important? If you remember from DC circuit, I mentioned that op amp is an active device that is able to amplify the signal. So if we apply a signal with the amplitude of like A, the output amplitude can be greater than A. Okay, it can amplify the signal. So it's the reason we say these filters can have gain greater than 1 because they have an active device which is op amp. And we don't need inductor. They do not require inductor, which can be large and expensive. Large and expensive in low frequency applications. So we can like implement any active filter using capacitor and resistor and op amp. So we don't need actually to have inductor. Why we shouldn't use inductor? Because as I mentioned here, it can be expensive and very large, especially for low frequency applications. Okay, so any system, let's say this one is a filter or any system, I call it system, or it can be filter, no matter. So any system has input and output. Okay, so input and output, and always the ratio of output to the input is called the transfer function. Transfer function. So we can say in sinusoidal steady state, the transfer function. What is transfer function? T of j omega. Why j omega? Because it's a sinusoidal and it is a complex number. Okay, we show it with j omega. The transfer function is the complex output amplitude over input amplitude. Okay, so transfer function is VO over VI. So in sinusoidal state, the transfer function T of j omega determines the amplitude and phase angle of the output through the gain function. Okay, so before I say what is gain function, let me just explain it. So here the gain T of j omega is a complex number. Of course, any complex value has amplitude and phase. Okay, and we definitely know how to determine the amplitude and phase of complex numbers. So here we say the the amplitude and phase angle of the output through the gain function, which is the absolute value of t of j omega, okay, and phase function theta of omega is equal to angle of t of j omega. Okay, just it's a simple concept. This one is a simple concept. We know any like a complex number has an amplitude, which is the square root of a real part square plus imaginary part square, and phase, which is arctangent of imaginary part over real part. So it says that when we get a t, instead of replace z with t. Okay, so let me just replace z with t. So let's say t is a complex number. Okay, so if t is a complex number, which is the amplitude of t can be determined with this equation, and the phase can be determined by this equation. Okay, so we can say the amplitude gain and phase function theta of t can be determined by these two equations. Which equations? We can say output amplitude is the amplitude of the gain multiplied by input amplitude. Okay, so amplitude gain, output amplitude is equal to amplitude gain times input amplitude. Okay, so output phase is equal to theta of omega, which is the phase of the transfer function, plus input phase. Okay, so when we found t of j omega, when we got t of j omega, we can easily calculate the amplitude of t of j omega and the phase of t I j omega. And from these two, we can find, using these equations that you see here, we can simply find output amplitude and output phase. Okay, and we have like a phrase called frequency response. The frequency response is like a frequency dependent relationship between the input and output. The frequency dependent relationship between input and output is called frequency response. Let me just write it down. What is frequency response? We can say the frequency dependent relationship between sinusoidal input and the resulting steady state output is called frequency response of the circuit. Okay, and some more definitions in the filter. We have something called passband in the filters. What is passband? Passband is the range of frequencies with nearly constant gain. It's called the passband. So at the output, at the output, the like a range of frequencies with nearly constant gain is called the passband. The range of frequencies with nearly constant gain is called a passband. Okay, we have another definition which is stop band. What is the stop band? The range of frequencies with significantly reduced gain is called the stop band. The range of frequencies with significantly reduced gain is called stop. We have one more definition which is called cutoff frequency. Cutoff frequency. What is the cutoff frequency? The frequency associated with the transition from a pass band to an like adjacent stop band is called cutoff frequency. Okay, so the the frequency associated with the transition from a pass band to an adjacent stop band is called the cutoff frequency. Let me write it here. We can say the frequency associated with the transition from a passband to an adjacent stop band is called the cutoff frequency. how we like show cutoff frequency denoted by omega of C or F of C. Okay, so if we see subscript C, it means that it is cutoff frequency. Okay, now let's see, like for any of these filters, active filter or passive filter, let's see how many different type of filters regarding like a low pass filter, high pass filter, how many different type of filters we do have. We have the first filter, which I'm going to show here, is low pass filter. It can be like either active or passive filter. So low pass filter is not the like the it doesn't define the components of the filter. So active filter, passive filter determines if the filter can have a gain greater than one. Okay, so that one is like determine the gain amplitude. But here we are talking about the frequencies that are allowed or banned from entering to the circuit. So we have low pass filter. Here is a low pass filter if we x axis is frequency and y axis is gain. For a low pass filter, we will have something like this. So if see that by increasing the frequency, the gain decreases. Okay, the gain decreases. So from this point, we have two areas. We have passband, which the signal is allowed to pass through the filter, and we have a stop band. Okay, and where is the cutoff frequency? F of C is here, cutoff frequency. So this one is low pass filter, which allows the frequency less than FC goes through the circuit. So the next filter we are going to learn is high pass filter. So high pass filter. What is high pass filter? High pass filter allows frequencies higher than like cutoff frequency moves through the circuit. So here frequencies less than cutoff frequency is called stop band, and frequencies greater than cutoff frequency are called passband. Okay, the next type of the filter is like band pass filter. Band pass filter. So let's see what is band pass filter. Band pass filter. So here we have frequencies, we have gain. Band pass filter has two cutoff frequency. Cutoff frequency low, cutoff frequency high. It allows the frequencies between these two cutoff frequencies go through the circuit. So it like the response is like this. It has two cutoff frequency, one here, one here. F cutoff frequency low, cutoff frequency high, and of course between these two cutoff frequency we have passband. the other two frequency ranges are stop band. Okay, so you see frequencies between these two cutoff frequencies are allowed to go through the circuit. The last type of filters is is band stop filter. Band stop filter. What is band stop filter? Also, it has two cutoff frequencies, and here is band stop. You see, it has two cutoff frequencies, one here FCL, one here FCH, and of course between these two frequencies is a stop band, and the other two are pass band. Okay, so you see all four different type of filters that we can implement. We can like make or like build all these filters in active form or passive form. If they are in active form, the maximum gain here, the maximum gain is less than 1. If they are passive, if they are active, the maximum gain can be greater than 1. Okay, let's move on and talk about the cutoff frequency. So I say cutoff frequency is this frequency. So it should be like I'm talking about this figure. So cutoff frequency should be here, or should be here, should be here, should be here. Okay, where is the exact location of the cutoff frequency? Because as we see, let me erase this additional. Okay, because as we see, the response is not very sharp. If the response was something like this, 0 and 1, we definitely say that cutoff frequency is here. But because it changed gradually from 0 to maximum, we should determine a location, like a frequency that we call or define as cutoff frequency. Let's discuss it. So cutoff frequency. Okay, there is a very simple and important definition to determine the cutoff frequency. We say cutoff frequency is the frequency at which the passband gain decreases by a factor of 1 over square root of 2 from its maximum. So if here in this figure, if here is maximum, okay, the cutoff frequency is a frequency that the passband gain decreases by a factor of 1 over square root of 2, which is 0.7. So if here we have 1 over square root of 2, like factor decrease in the amplitude, we can say this frequency is cutoff frequency. Okay, so let's go ahead and determine the different cutoff frequencies. So by the way, let me just, for example, here show you the example. So here, if this one is a cutoff frequency, so this gain, this gain should be equal to 1 over square root of 2 times, and here we call it V, like we call it, uh, let's say, maximum value. So maximum max. Okay, so maximum value. So this amplitude should be 1 over the square root of 2 of max. Okay, so this one is the cutoff frequency, 1 over the square root of max. Okay, let's go ahead and write the definition and see some examples. We say cutoff frequency is the frequency at which the passband gain decreases by a factor of 1 over square root of 2, which is equal to 0.707 from its maximum value. Okay, so the cutoff frequency, we can say the amplitude, the gain of the cutoff frequency T of j omega c, c stands for cutoff frequency, should be equal to 1 over square root of 2 of T max. Okay, which where T max is the maximum gain in the passband. Okay, so let's show it in a graph. Okay, so here is gain, which is the amplitude of j omega, and here is the signal, not the signal, the frequency response. And if here is T max and here is 0.707 of T max, or 1 over the square root of 2T max is here, we just determine the frequency of this point and we go like this and we call this one as a cutoff frequency. Okay, so this one is a cutoff frequency. So how we determine cutoff frequency is the frequency that the gain is like 0.707 times T max. Of course, this region for this filter is called passband, and this region is called stopband. Okay. Now that we learned about different types of filters, let's try to design some filters. Okay, so we start with passive filters. Example. Consider the following RC circuit. RC circuit means a circuit that contains a resistor and capacitor. RC circuit. Find the relationship between output voltage, output voltage phasor to input voltage phasor, which is called gain. Plot the magnitude as a function of frequency. Okay, so here is the circuit. So we saw so many circuits so far, AC circuits, but do you believe this simple circuit which includes only one resistor and one uh, capacitor is in fact a filter? Yes, any circuit including including resistor, capacitor, or inductor acts like a filter. So we should be careful when we design a circuit for AC applications. So they might filter some frequencies, so block some frequencies. So we always need to study the frequency response of any AC circuits. So here is the circuit, and we want to find the gain, which is the relationship between the output voltage phasor to input voltage phasor. The simplest way, as we learned so far, is voltage division. So this one is the same as ZC, okay? Same as ZC. So we can say VO is, which rules we should use here? Voltage division. So it's equal to ZC, which is 1 over J omega C over the total impedances R plus 1 over J omega C time Vi. Okay, so we can say Vo over Vi is equal to 1 over J omega C in the denominator with J omega C 1 plus J omega C R, which is equal to 1 over 1 plus J omega RC. This one is the gain, T of J omega. So we got T of J omega for this circuit. So gain, which is the amplitude of VO over VI, is equal to 1 over square root of 1 square plus omega RC square. Okay, so that we reach to this point, so this one is a relationship. Now we want to plot this by letting omega takes values from 0 to infinity. So omega from 0 to infinity, we plot the magnitude. So first let's just make a table, omega and gain, which is VO over VI, omega and gain. What about omega 0? If omega is 0, here is 0, 1 over 1, is 1, so gain is 1. What if omega is infinity? If omega is infinity, this like term will be 1 over infinity, which is equal to 0. Okay, so if omega is infinity, gain is 0. What if omega is 1 over RC? 1 over RC. Let's substitute, like replace omega with 1 over RC and see what would be the, what is the output. 1 over 1 over square root of 1 plus, instead of omega, we say 1 over RC times RC square, which is equal to 1 over square root of 2, which is 0.707. Does it remind you anything? Of course, yes, it is the cutoff frequency. So we say 1 over RC is cutoff frequency. And the gain is 1 over square root of 2, or 0.707. Let's just find one more point. Let's calculate 10 over RC. So if we calculate 10 over RC, so in this here we say 10 over RC, which will be equal to 1 over square root of 1 plus 100. So 1 over square root of 101, which is equal to 0.09. So we can say the gain is 0.09. Now that we have these 4 points, we can plot the frequency response. So this one is gain, this one is omega, and then no matter if you use omega or f, because we know that omega is 2 pi f. Okay, they have a linear relationship. Okay, so we need to define different frequencies. So omega c, let's say it's here, 1 over RC, 1 is here, and let's say 0.707, which is 1 over the square root is here, and we now it's time to complete the frequency response. So this one is the complete frequency response of the circuit, and this one is passband, and this one is stop band. Okay, so we had this circuit. We had no idea of what kind of filter it is. So we plotted the frequency response. Now we know what kind of filter it is. It is a low pass filter. It is a low pass filter. Okay. With a maximum gain of 1. Let's see one more filter example. Consider the following RC circuit, and of course find the frequency response. So this time we have this circuit. This is VI 1 over j omega c r and VO. Okay, so this one is the new circuit. We want to see what is the frequency response and what kind of filter is this filter. Okay, so let's do that. We say VO again, voltage division. VO is this time is equal to R over R plus 1 over J omega times VI. The result, we can say VO over VI is equal to R over 1 plus J omega RC over J omega C, which is equal to J omega RC over 1 plus J omega RC. So this one is the gain, T of J omega. So gain is equal to absolute value of this number. So it is the absolute value of numerator, which has only imaginary part, of course, is square root of omega RC square. For denominator, it's equal to 1 square plus omega RC square, which is equal to omega RC over 1 plus omega RC square. Okay, now we got the gain. Let's just plot the gain. Again, the same table. Gain, sorry, omega on the left column and gain the right column. So omega 0, omega infinity. If omega is 0, the numerator is 0, denominator is 1, so 0 over 1 is 0. So the output is 0. If omega is infinity, so we'll have infinity over 1 plus like infinity. So we should just find the value of this fraction, because we know that infinity over infinity is like undetermined. So we need to solve this limit. So if we say omega RC over square root of 1 plus omega RC square, when omega goes to infinity, we know that this term will be very large compared to the first term, so we can ignore 1. So it will be equal to omega RC over square root of omega RC square, which is equal to omega RC over omega RC is equal to 1. Okay, so algebra. So this one is like finding the limits. So if omega goes toward infinity, the output is 1. What if omega is 1 over RC? If omega is 1 over RC, let's just find the output. Okay, so it will be equal to, instead of omega, we put 1 over RC. So 1 over RC times RC over 1 plus 1 over RC squared is equal to 1 over square root of 1 plus 1, which is 1 over square root of 2. So it's equal to cutoff frequency. So omega C, the same as low pass filter, we see that if we put omega C equal to 1 over RC, the gain will be 1 over square root of 2, or 0.707. What if like we put omega equal to 10 RC, we will have 0.99. So now, based on this information, let's plot the frequency response. Omega gain omega C, which is equal to 1 over RC. The maximum gain we know is equal to 1. And of course, we have 1 over square root of 2, or 0.707. Okay, for the frequency of 0, I said that the gain is 0. For frequency of infinity, gain is infinity. Gain is 1. So this one is the frequency response. What kind of filter is this? It's high pass filter. Okay, so this one is a high pass filter. But one more thing that Ivan mentioned is regarding determining the type of the filter by looking at the circuit. If we look to this circuit, there is something that we should know. We know that the capacitor is zero or short circuit for DC signals. So if omega is 0, the capacitor, sorry, if omega is infinity. If omega is infinity, ZC, let me just write in a different way. Let me just write it here. We know that Z of C is equal to 1 over J omega C. Okay, so this one is the impedance of a capacitor. If omega is equal to 0, what's going on? ZC will be equal to infinity, so acts like an open circuit. So for frequency 0, the capacitor acts like open circuit. If frequency is infinity, the impedance of the capacitor is 1 over infinity, which is 0, acts like short circuit. So we can say for omega 0, capacitor is open circuit. For omega infinity, capacitor is short circuit. Using this information, we can determine the type of the filter by just looking to the circuit. So here it's the circuit. Let's just guess what kind of filter is this circuit without solving it. So we have a capacitor here. If the frequency is 0, this capacitor acts like open circuit. When it acts like open circuit, it means open circuit. So what is VO? VO is not connected to Vin. So VO is 0. So for omega 0, VO is 0. Now let's continue. Let's put the capacitor back. Now we want to discuss or analyze this circuit in frequency infinity. If omega is infinity, I said that this capacitor will act like short circuit. Okay, what is VO in this circuit? If you look, there is a wire connecting these two parts, so both are like the wire. As always, it's like nothing, it's just a connection. So VO, this node is directly connected to the voltage source, so VO definitely is equal to VI. So VO is equal to VI. So we see that for omega 0, gain is 0. For omega infinity, gain is 1. So what type of filter has gain 0 for frequency 0, gain 1 for frequency infinity? Of course, high pass filter. Okay, let's do the same like calculations or the same analyzing for the other circuit we have here. Okay, let's see. Let's say omega is 0. If omega is 0, the capacitor is open circuit. What is the voltage? There is no current. It's open circuit. There is no current. So when there is no current, both sides of the resistor have the same voltage. So the other side also has the voltage VI. So these two are same. So as a result, VO is equal to VI and gain is 1. Okay. Now let's go back to frequency infinity. If this is a capacitor and we say frequency is infinity, what is VO? If the frequency is infinity, the capacitor acts like a short circuit. It's a wire. So we see that these two terminals are connected together with a wire. So there are like they have nothing with the rest of the circuit because these two nodes are connected to each other using this wire. So the voltage, of course, is 0 because they're connected to each other. So there is no resistor or nothing between them. So VO is 0 and gain is 0. So what kind of filter is this? A filter that has a gain of 0 for frequency infinity, gain of 1 for frequency 0. Of course, it is a low pass filter. Okay, so by looking to the circuit without like solving the circuit, we can easily determine the type of the filter. Okay, in the next lecture, I will talk about the active filters.